And we're pleased to have today Dr. Jim Bell. Dr. Bell is a professor in the School of Earth and Space Exploration at Arizona State University in Tempe, Arizona. He's also a distinguished visiting scientist at NASA's Jet Propulsion Laboratory. And so he's actually worked on a lot of the Mars missions, a lot of the rovers. As a matter of fact, he is the principal investigator for the Mastcam-Z cameras on the Perseverance rover. And so I followed his career since the Mars Pathfinder days. I'm really happy that you're on our call today, Jim, and we'd love to hear what you have to say today.
Sounds great. Thanks, James. Can you hear me okay?
Yes.
Okay, great. All right. Hey, everybody. Sounds like you guys are having a pretty exciting summer on Mars. Hopefully you've all brought sweaters because even summer on Mars is pretty cold. I'm Jim Bell, professor at ASU, as James mentioned. Been involved in Mars rovers since there were Mars rovers, back to Pathfinder and Sojourner rover. Was the camera lead for the PanCam instruments on Spirit and Opportunity, which may have landed right around the time some of you were being born, back in 2004, and deputy lead of the cameras on the science cameras on Curiosity rover and lead of the science cameras on Perseverance. So camera guy, trained in geology and astronomy as an undergraduate and a graduate student, and just a super space nerd my whole life, probably like many of you. Let's see if I can figure out how to share my screen. And you're going to have to tell me, are you seeing my screen? And tell me if you're seeing it in full screen mode.
Yes, let's do.
Yes. Okay, great. So I'm going to tell you some stories and some updates on what's going on with specifically with Curiosity and Perseverance. I mean, we could talk for hours about the sort of history of Mars exploration, right? Here's a great shot that I like, put together by some of my Planetary Society colleagues over the years. And it goes back all the way back to 1960, right? When we say we've had a lot of missions to Mars, and I don't mean just we like NASA, I mean globally, 47 missions by 8 different nations or organizations of nations like the European Space Agency, right? So many, many, many attempts throughout the entirety of the space age, back to 1960, right? And look at that number in lower left, more than 40% have failed. It's difficult. Mars presents specific and difficult challenges, right? Much farther away than the moon, thick enough atmosphere that you have to deal with it getting down to the surface and frictional heating and all that, but not thick enough to just use parachutes. So you need some sort of active retro rockets and all that. And very excitingly, out of those 47 missions, 10 successful landers or rovers, 10 now on the surface having operated successfully. And this is a nice shot of the 10 of them. 4 of them, Curiosity, Insight, Perseverance, and the Tianwen lander / rover, those systems are still working. And really, I'm going to focus on 2 today, just Curiosity and Perseverance, the ones that I'm most heavily involved with sort of on a day-to-day basis as part of my job. So today's story is about those missions. It's a story about this enigmatic planet, right? And you guys have been studying it, I'm sure. We see Mars through telescopes, bright areas, dark areas, polar caps. You know, we get a sort of a global view from ground-based and Hubble space telescopes. Certainly JWST will start looking at Mars here pretty soon. It's within its capabilities. That's going to be exciting. But much of what we know, most of what we know, comes from being there in orbit or on the surface with a lander or a rover. And that history goes back a long way, right? Mars has this thin atmosphere, but it also has this heavily cratered surface, right? It's almost like the early history of Mars exploration was kind of like, is Mars just the moon with a thin atmosphere? And some of the early missions gave that impression because they flew over the south the hemisphere heavily cratered terrain, and didn't see evidence that Mars was this dynamic and enigmatic place. until Mariner 9 and Viking in the 70s really got to know the place at high resolution and discovering the tallest volcanoes in the solar system, the most extensive and deepest canyon systems and river networks out there, and ancient terrains on Mars that show evidence of water, and even relatively young terrains on Mars. This is the side of a gully. This is the side of a crater, some gullies in the side of a crater. This whole area is only a couple of football fields across, and you can see lots of evidence for subsurface water flow across the surface, even potentially in modern times. So there might be groundwater, there could be aquifers, there's certainly buried ice. We don't know the heat flow, so we don't know how or whether that ice is being liquefied into liquid aquifers and escaping out the surface, et cetera. So all of these are critically important questions that we're trying to get at with Mars exploration, right? But the one sort of overriding theme that you've no doubt heard about, right, is that Mars is this cold, dry, barren, lifeless on the surface, as far as we can tell, world. But if you turn the clock back 2, 3, 4, 4.3 billion years ago, 4.5 billion years ago, it was a lot more like the Earth. That's the evidence that we've obtained from these space age, space era discoveries. And maybe it was never like this. This is an extreme example. An artist has taken all the low areas and filled them in with water and turned Mars into an ocean world like the Earth is. There are some people in the community who think maybe Mars was this warm and wet. I think most don't. I think most people think it was much, much more isolated. It is, 50% farther from the sun. After all, it is much colder. After all, it is difficult to maintain a thick atmosphere and internal heat on a smaller planet than the Earth for the entire history of the solar system. So maybe Mars wasn't like this wet, but there were rivers, there were lakes, there were at least probably small seas, if not oceans, on the planet. And that evidence is preserved in the geology and mineralogy and geochemistry that we can study on Mars directly today, and through telescopes and through meteorites that are from Mars, right? So that's the driving thing. What was it like, right? Was it a habitable world? Was it an inhabited world, right? Step beyond habitable, but inhabited, different question. And for how long was it like this? And did life get a start here like it did on the Earth? And if it did it get a foothold and become, did it evolve and become complex? Did it retreat to the interior where it could still be today in the subsurface? These are just critically driving questions, astrobiology questions. And Mars has the best combination of potentially Earth-like conditions and accessibility in the solar system, right? We can talk about Europa, of course. We can talk about Titan. We can talk about Enceladus. These are all great, important astrobiology hotspots, difficult to get to, much more difficult compared to Mars. So it's that combination of astrobiology potential and accessibility that have driven those 47 missions, and that will continue to drive missions into the future. And I'll come back to the future a little bit. And so there's been some amazing robot geologists that have been part of those 47 missions. We can't go ourselves yet. There's a lot of us want to go. We can't. So we send avatars made out of silicon, aluminum, copper, titanium, and we send them with equipment and with senses and capabilities that mimic some of the things that we would do and some of the equipment that we would bring. You see the next step up to Curiosity, about the size of a Mini Cooper, and then most recently Perseverance, and the completely separate lander and robotic vehicle Ingenuity that's been operating successfully on Mars since February of 2021, along with Perseverance rover. So, we build these very sophisticated robots. Perseverance mostly built from spare parts from Curiosity. That's how NASA could fit it into a very constrained budget that NASA has compared to certainly the rest of the federal government. So lots of economizing, but as you'll see, with a very different mission. And then you combine those capabilities, vision, sensing, with a really important thing that all field geologists want, and that's mobility, right? And that was the first thing that was demonstrated with the Sojourner rover back in '97 was the ability to drive across the landscape and the ability to drive over obstacles. This is an animation showing this really elegant rocker bogie suspension system. Many, many different ways you can solve this problem, right? You can use treads, you can use wheels, tires, you can walk, you can hop, you can fly, but however you do it, mobility turns out to be critical. And you can really enhance the capability of your mission compared to having a stationary lander, right? And we're seeing that, much more recently in Curiosity and Perseverance. Here's some movies of Perseverance just before it left JPL in 2020, heading for the launch pad in Florida that summer. And you can see it. They don't move fast. They're slow and steady, kind of tortoise-like, but they do have the capability to get us from place to place. And we've driven all of these vehicles many tens of kilometers across the surface now, really, acting like we would, right? You get out into the field in some remote field site, helicopter drops you off. You're not just going to stand there, look around. You run up to the highest hill, do some reconnaissance, go get some samples over there, go study that geologic contact, whatever. And so we're able to recreate some of those capabilities in these vehicles as well. And you have to carry sophisticated science instruments, right? And so you load these systems up with the best that we can. They fall short of what you can do in the best laboratories on the Earth, because of course you don't have the restrictions of having to put your mass spectrometer on a rocket in the laboratory, right? You don't have the restrictions of mass, volume, power, data rate, all of those critical resources, money, all of those critical resources that constrain you, that you're all running into, no doubt, as you start thinking about your own missions and your own ideas. They put you in a small box compared to what you can do on the Earth, and yet we can still send sophisticated laser instruments, sophisticated weather instruments, sophisticated cameras, drills, microscopes, radiation sensors, mineralogy sensors, geochemistry sensors. So that's really cool. And a lot of that comes from the university community. A lot of it is, I'm a professor at a university. NASA put out a call for instruments on these rovers, like the Perseverance rover. And they tell you, here's the resources, here's how much volume, mass, power, data rate, money you have to deal with. So you tell us, scientific community, university community, federal research lab community, what can we fly that's going to answer these important science questions about Mars? And so we wrote a proposal, and we competed with 25, 30, 40 other teams from around the world for instruments. And we were lucky enough at ASU to get selected to build and run the Mastcam-Z cameras on Perseverance. So I'll show you some examples when we get to that. Now, the other part of this is, where do you go, right? And it's a big planet, smaller than Earth, but big in the sense that there's the same amount of land area on Mars as all the continents of the Earth put together, right? So that's a big space to choose from. We can't land anywhere. You can't land at the tops of the volcanoes. There's not enough atmosphere for the parachute to work at all. You can't land at the bottom of the rocky canyons where there are boulders or sand dunes that would bog you down. We can't land at too high of a latitude without special equipment, because it gets dark, like in the Arctic and Antarctic on the Earth for part of the year, because it's super cold. Temperatures get down to the condensation point of CO2, and it snows out of the atmosphere as those dry ice polar caps. So you need so much power to keep those systems warm. And so lots of constraints on where to go, but still it's a big planet. And we've got all these amazing orbital data sets now from a few decades of that kind of work with NASA orbiters and other countries' orbiters. And so all of that goes into a landing site selection process. You have these meetings invite the whole world, and you get 50, 100 people show up with 50 or 100 different landing sites that they want to go to. And, the engineers will say, no, can't go there. No, can't go there. Too high, too low, too rocky, too sandy, too cold, et cetera, et cetera. And then you have another meeting, 6 months later, and it's winnowed down to 30. And then another meeting, and it gets down to 10. And over the course of several years, you bring this community together, the scientists, the engineers, the managers, the administrators, and you just it gets into a collegial fight, shootout, right, about where to go. And so that's where the science comes in. That's where, hey, let's try to find somewhere that has astrobiology potential and can tell us about that past climate and the connections between early Earth and early Mars, and whether the environment was habitable or perhaps even inhabited. And that's how these sites were chosen for Curiosity and Perseverance. Both of them are inside craters. Both of them are places where there's lots of sediments inside those craters. They were crater lakes at one point in time, and sediments were deposited in those lakes in both gentle and violent environments, and in some cases making a huge mountain of sediments, as in Gale Crater, Mount Sharp. In other cases, a delta of sediments that we see in Jezero Crater. And so we have evidence that there was liquid water there, evidence that there were relatively long-term geologically watery environments, lakebed environments, maybe gentle sedimentation, depositing ancient materials, minerals and rocks from the ancient highlands of Mars that might contain evidence of early signs of life, textures, geochemical evidence. I will say, honestly, nobody's expecting to find fossils. That would be phenomenal. And of course, if we find them, nobody's going to complain, but nobody's expecting it, right? Because remember, if those of you who study geology, the fossil record on the Earth only started 550 million years ago. Before that, it's all soft-bodied and single-cellular, multicellular colonies of multicellular organisms like stromatolites. And the evidence for early life on Earth is not fossil evidence. It's textures and chemistry and mineralogy and isotopes, things like that. So that's kind of where these payloads are focused on. Just so you know, nobody's expecting to find real macroscopic fossils, but there's lots of other lines of evidence, biosignatures that you've probably heard about that folks are looking for with these payloads. So I'll start first with Curiosity, give you a little update on what's happening with that mission. This is the view from the ground of that mountain of sediments, just a spectacular vistas at this landing site. And over the course of now 3,533 days on Mars, so almost 10 years, it'll be 10 years in August since Curiosity landed. We landed at the start. I don't know if you can see my cursor. Can you guys see my cursor? Anyone?
Yes, we can see
yes.
it. Yes.
Okay, great. So we started out in the plains here where the ellipse is relatively flat, relatively rock-free, safe place to land. And we've driven more than 17.5 miles, more than 28 kilometers across the plains through these, winding our way through these sand dunes, which are taller than the rover, and making our way up the slopes of this big mountain. And the cool thing about this mountain of sediments is that the top of the mountain of sediments is higher than the rim of the crater. How do you do that? Right? Is a big mystery here. Was this whole thing filled with sediments? Even above the rim, the whole area was sedimentary, and then it's all been kind of eroded down. It's a mystery story here. And the mineralogy, the kinds of rocks and minerals changes as you go through these layers. And we're encountering those changes with the rover. And we're encountering right now this contact between the older material at the bottom of the stack, which is more hydrated, more loaded with clays and minerals that contain some of that ancient water built into their mineral structure. And as we get higher up, we see more anhydrous kinds of sulfates and oxides and other minerals. So somewhere around where we are now, there's this big change in climatic conditions. And that's the part of the job of this rover, is to do that, walking up the geologic cross section like we would do in the field, taking samples, making measurements all along the way. And so we've seen a lot of really cool things right where we landed, out where we thought, it's just going to be kind of boring and flat and safe, because that's where the engineers want us to be, to land safely, and everybody wants to land safely. Even there, we started seeing first evidence for what are called conglomerates, loose rounded pebbles cemented together by clays or sulfates or some kind of cementing agent. This might look a lot like if any of you have helped pour a concrete slab. in your backyard or your sidewalk or something. It kind of looks like this. You do the same thing, right? You take a bunch of rocks and you mix it in with some cementing agents, and you put some water in, and all of a sudden you get this hard cement. And the cool thing about these rocks and pebbles is that many of them are rounded. And so it provides evidence right where we landed that indeed there was water flowing through here. There were, rivers and currents and streams that were rounding the rocks that were coming down from the hills, the ancient hills around us. So that was super exciting to see that initially, to see evidence on the ground, so-called ground truth, that what we were thinking is happening from orbit might actually be happening when you get to the ground, because that's not always the case. Even in Earth geology, using space images or airplane images, you get there and the ground truth might be different than the hypotheses that you were putting out earlier. So we've been using this great payload. And here's just an example. I show a lot of pictures, but also, maybe some of you have studied spectroscopy or learned about spectroscopy in physics class or chemistry class or astronomy class or whatever, but we have lots of spectrometers on these rovers. And so it's much more than just pictures. We get a lot of what I call squiggly line science like this. And any of you who are familiar with astronomy will recognize these emission lines from different chemical elements. This is just like what we would see with a telescope with a spectrometer pointed at a star or a galaxy, right? We're seeing the emission lines of the individual elements. And what we do is we kind of create a little star or galaxy on the ground by firing a laser at the rock, and it zaps a little 100 micron spot and vaporizes it, ionizes it. And as that ionized cloud is expanding and cooling, you see these emission lines from the chemical elements there. And so you can get an inventory. How much aluminum, calcium, silicon, iron, potassium, all these important elements that go into forming rocks and minerals, and that tell us about the chemistry, the origin of these materials, and their evolution with time. So spectroscopy is a huge, huge part of what we do, even though it's not something that is easy to explain to the general public or that we feature a lot in sort of general public kind of media releases and press conferences. So lots of cool things. Again, from the surface, we found evidence for a variety of different rock types, a variety of places where groundwater was coursing through these rocks. These are fractured rocks. We're inside an impact crater. The whole thing has been busted up by the crater forming event, right? And so we have lots of ground fractures, lots of ways for water to travel through the subsurface and deposit minerals. So we see veins, fractures, and things like that. We see these beautiful layers of mudstones and sandstones, and it tells us, yes, sediments were transported across. Some of it was in suspension in the water and very gently settling out of the water to create that muddy lake floor. Beautiful places on the Earth to preserve biosignatures, by the way, because they're low energy. You just bury different kinds of minerals and chemical evidence and textural structures. And on the Earth, fossils, you bury fossils in those environments as well. So just a great environment to be exploring and really vindicate the idea from orbit that this really was a crater lake and that water was an important part of the environment here in ancient times. Of course, Curiosity has a drill. We can drill into the surface. We can scoop up some of that drill material, bring it into the rover and analyze it directly for chemistry, for isotopes, for organic molecules, and of course, take pictures and other measurements remotely of those materials. And now, almost 10 years later, we've drilled 35 holes on Mars. They're really not much bigger than your pinky, right? So we're not talking about drill rigs and all that kind of stuff. These are pretty small. But the cool thing that you can notice just from these pictures is if you can get below the subsurface, red Mars, the red planet, very quickly becomes gray Mars, the gray planet, right? The redness is a surface coating, a cover or an alteration coating of oxidized iron that, the famous Mars dust storms distribute that dust across the planet, and it settles and gets everything dusty. And maybe just a small amount of weathering, chemical weathering from the tiny amounts of water vapor that are in the atmosphere today are also producing some oxidation of the surface. But if you get below that, you start to see the primary minerals, the fundamental volcanic rocks that were formed in those environments. And we've done that 35 times now. This number 35 here was just from a couple of weeks ago. So very exciting to be, of course, sampling and getting the chemistry and mineralogy and all kinds of information all along the way. And this is exactly what we would do if we could go out in the field and collect these samples ourselves. We'd probably send them back to the lab. We'd have one of our graduate students run the analysis for us, but we would do this same kind of a very careful sampling and transect as we go up into the section. From an engineering standpoint, it hasn't always been easy. The rocks in this environment are extremely hard and tough. Many of them are not rounded. Many of them are jagged. So some of them are quite young. There may have been some volcanic deposits in here since those early days of lake bed, some ashfall deposits, a lot of glassy volcanic rocks and minerals, and they beat the heck out of the wheels of the rover. There, you can see big holes have been scratched and gouged out of the wheels. And we've had to really modify the way that we drive this vehicle and make it much more of a dune buggy, trying to stay on the softer stuff and avoid driving intentionally over the hard angular rocks as much as possible. But that traverse has been very successful. It's been, slow going. That's 17 miles to get up to the slopes that we're in now, right? How long would that take us? We could probably do it in a couple of days of hiking, maybe a good week if we're stopping and sampling. But almost 10 years to get this vehicle up there. And of course, we're not in real-time contact with any of these vehicles. We're not joysticking them. We're just sort of once a day sending uplink commands, and they go off and execute those commands and send us their results back. They go to sleep at night to hunker down and stay warm in the extremely cold nights. We process the data and figure out what to do tomorrow. They wake up, we have a new list for them ready to go the next morning. And we've been doing that with all of NASA's rovers operating that way since back in Sojourner days. So the views, like I said, absolutely spectacular landscapes, driving up through these slot canyons, looking at these beautiful layered rocks, many of which have these mineral-filled fractures, right? These are easily recognizable by geologists who study earth rocks, who study the way groundwater moves through fractures and mineralizes. These are, sulfates and clays and carbonates in some places that are telling us about the conditions of the water, its pH, the conditions and timing of formation. Just a rich trove of information about the environment comes from the minerals. Minerals form in response to their environment. It's true on the earth. It's why, the soils in Brazil are red and the soils in Iceland are black. It's minerals form in proportion to their environmental conditions, just on Mars, just like on the Earth. So we use them as mineral indicators. Just a nice zoom up of some of these calcium-filled veins here. So groundwater coursing through these rocks and depositing those minerals in these units. Now, most recently, we've been driving higher up into these rocks, and here's some pictures just from the last few weeks, and this one just from the last few days. We're encountering these rover-sized boulders that are shedding out of the cliffs in this mountain of sediments that we're driving through, but continuing to do that, just very methodical sampling of that material and trying to find evidence for that climate change and more details about how long it took, why it happened, and what were the conditions like. Was it something relatively sudden? Was it probably much slower and gradual? We know climate changes happen on the Earth over slow, gradual, as well as sudden time periods driven by impacts, volcanism, or changes in the Earth's orbital conditions, or all of the above. But no climate change like this magnitude has ever occurred on the Earth. Earth has always been habitable, always been warm and wet, except for potentially relatively brief periods of planetary glaciation. Still warmer and wetter than Mars today, or perhaps that Mars has ever been. So, the magnitude of the climate change that has happened on Mars is stunning, and it's kind of important from a planetary perspective for us to understand that and learn about the potential for our own climate. So that's a quick update on Curiosity. Let me try to do the same thing for what's going on with Perseverance, but just stop for a second. James, any questions pop up?
I don't think we have any so far.
Okay, great. All right, let's dive into Perseverance then. The sister or brother rover of Curiosity, again, made from spare parts, but with a different payload and a very different mission. The similarities in the mission, geologic exploration, picked an interesting landing site I'll talk more about in a minute, looking for habitability and biosignatures, that's also very similar. One big difference, right? The drilling done on Curiosity is to bring samples into the rover for analysis. The drilling is drilling and coring on Perseverance to bring a core sample into the rover, to hold on to it for a bit, and then eventually cache it on the surface. And a future mission, and I'll talk about this at the end, the future mission will collect those cores and bring some subset of them back to the Earth. So not just drilling, but preparing a returnable cache of drilled samples. And then, of course, preparing for human exploration as well. But this sample return aspect is the totally unique thing and new thing in Perseverance. It's what separates this mission from everything else that's flown before to Mars, in that it is intended to be the first part of it, at least a one, but potentially many decade Mars sample return mission. And that's super exciting for all of us involved. So launched in the summer of 2020, landed in February 2021, and we've been operating for almost 500 Martian days. We're coming up on Sol 500 this weekend on Mars. So it's been a great mission so far. I know many of you probably follow along. This was a fun plot to put together. Remember, I mentioned those 10 successful missions to the surface. Here's where they all went. And you can see this quite a cluster around where Perseverance and Curiosity are. The Chinese lander and rover not too far away, off in the plains of Utopia, but that's where Perseverance is. And we landed inside of a crater, again, similar to Curiosity, this crater called Jezero. And the cool thing about Jezero crater is that it has several, but one in particular, super interesting delta fan of sediments that have come out of the crater wall in the west here and fanned out across the surface in what we believe was happening in water in a lake, kind of like at the end of the Mississippi River. You've got the shallow, gentle Gulf of Mexico there, and those Mississippi River sediments come down and they fan out into the Gulf and they create the Mississippi River Delta, or the Mekong River in Asia, right? And we think the same kind of thing was happening here, and we see lots of classical, meanders and spurs and evidence that tells geologists, hey, that looks like a river delta. And what a great environment to look for evidence of preserved habitability or inhabitation, again, if we get so lucky, right? So the goal, again, was to land in a relatively safe part of the crater, relatively flat, relatively safe, and then drive over to the primary target, which was the delta. And so that's actually what we did, landed in a relatively flat, safe part of the crater. And many of you probably seen the movies taken from the rover, looking up, looking down, just unbelievable, right? Parachute, retro rocket, sky crane maneuver, getting down to the surface. And the last few kilometers to the surface, we were actually targeted for this region called Seta here. And you, even in this orbital image, you can see the sand dunes. There's a lot of big sand dunes in here. And the onboard autonomous imaging system recognized this area as dangerous from the standpoint of mobility, right? We probably could have landed there, but then you get stuck like a lobster in a lobster trap. You can't get out of the sand dunes. And so this onboard system and the autonomy diverted us. And it could have diverted us towards the delta or away from the delta. It chose away. So, okay, you got to land safe. And this environment here, I'll show some pictures in a minute, much more benign for us to land in. But it meant that we're pretty far from the delta, only a couple of kilometers, but we can't drive across this stuff to get there. We have to go around it. So we knew even right after landing, hey, we're in for quite a traverse to get to where we want to go. And we actually chose to go the other way for a little while to get into this stuff, this areas, not only sand dunes, but it seems to be a fundamental different kind of rock type, fundamental different kinds of minerals in this environment. And so we wanted to characterize it, and it was not possible to get through the sand dunes here. We went around, did a sort of a toe dip in there, took some measurements, took some samples, collected some samples, of this material we landed in here as well, then turned around and booked it back, went back past the landing site and all the way around over the past few months. And now the rover is up here at the Delta front. We're finally where we'd been dreaming of being more than 5 years ago when we first saw and proposed, some of us, this landing site as a place to send Perseverance. So let me just share with you some of the views from the ground then. This is the landing site itself. You can see some of those big bright spots or the scour marks from the retro rocket engines as we were coming down. But just like for Spirit, Opportunity, Curiosity before, the engineers helped us find a relatively safe, benign spot. No big boulders here, no big sand dunes, a pretty safe place to land. And we could see the Delta pretty close by. Nearby, there's pretty rocky places that would have been tough to land in. We can use our infrared filters on the camera to create false color composites and get a sense of the variation in the composition and mineralogy. We use images like this, mosaics like this, as triage all the time. We cannot sample every one of these rocks. We can't zap every one of these rocks with the laser chemical analysis tool that Perseverance has. It's very much like Curiosity's. There's just too many of them. So you use the cameras and the fact that we can cover this wide span of real estate around us in multiple filters, multispectral filters, to do that triaging of what's going on around us. So that's part of what we do with the Mastcam-Z cameras. Partly, we also use their high resolution. So even though we're still several kilometers away, we can dial up the zoom in the cameras to full resolution and get these initial, right after we landed, beautiful mosaics of the front of the Delta. And we can see the layers in the front of the Delta on edge that we could only see from above in orbit. And even some of these remnants, I pointed out a Delta remnant called Kodiak earlier, and this is what it looks like from the ground. We think the Delta was much more extensive, and it's eroded back over billions of years, leaving in some places pieces that just haven't fully eroded away. And that's what we think Kodiak here is. And so it's a bit of a tease because we could see these back in February of 21 at a distance. We knew we couldn't drive straight there, so we knew we were going to have to go around. And so you can imagine how satisfying it is right now that we're there poking around at the fronts of these Delta deposits. Oh, there's Kodiak right there. That's what it looks like from orbit. So that's that knob. It's about 150 meters wide, about 40 meters tall. So it's a pretty big structure. And we may approach it eventually. Kodiak is one of the places where we got some of our first science results. You can see these beautiful layers in the rock, these Delta layers. We think that these are some of the sandstones and maybe mudstones that were deposited as the river's flowing down out of the hills, meandering, moving around, changing its environment, changing its slope, changing its speed. Punctuated through here, through some of these gentle layers, there's big boulders in here. And so there were giant floods that were happening as well, kind of intermittently with the gentle sedimentation. So the picture we're getting from the ground is much more complex than what we get from orbit, of course, because you're there, right? Again, ground truth doesn't always match your orbital expectations, especially when you can see things in obliquely that you could not see vertically from orbit. So we got some of our first results, published it in Science magazine last fall, and so that was pretty exciting. Now, remember Ingenuity, right? Ingenuity's hanging out along with this as a tech demo. First time we attempted powered flight on another planet. Mastcam-Z team was responsible for taking the movies. So that's what my team did at ASU, filming the first historic flight on another planet, April 19th, 2021, the sort of Kitty Hawk moment for aviation on aviation history on another world. Just did a simple little 3 meter height. You saw it turn about 90 degrees. You can see it fighting the wind a little bit there, right? And they're taking data and getting all sensor measurements there as well. this is, you can see the size of the helicopter in the picture with the technician at the upper right there. Pretty big, right? Almost 1.5 meter wingspan, almost 2,900 RPMs. You need big blades spinning super fast and a very, very light body to lift that thing in an atmosphere that's only 1% of the pressure of Earth's atmosphere. So it is possible to fly on Mars. It's challenging, but possible. And so we took a whole series of movies in spring of 2021, looking at the system and how it worked and how it exerted its own control on its flight. And it was doing a lot of autonomy in response to wind gusts. Is given a goal, get to this place, take pictures along the way, et cetera, et cetera. This is kind of interesting. We see it fly out of the scene, and we couldn't track it. And then when it came back, it's bringing all kinds of dust with it. It's like acts as a dust broom. The helicopter is creating such a vortex underneath it. And this is just delightful to the people who study how dust moves around and the surface atmosphere interactions. Lots of science coming out of this kind of accidentally, using the helicopter as sort of a human-made vortex machine. And we're also seeing lots of natural dust devils in this environment too. So that's pretty cool. And finally, we're using the helicopter as a scout, right? Here's some pictures from the helicopter. The sun's right overhead. So that's the shadow of the helicopter. Time-lapse photography, sending the vehicle to places we can't send the rover, like that sand dune rich area. So we have some great aerial reconnaissance now of that sand dune area. And we're demonstrating that you can use a drone like this, these kinds of vehicles, to enhance your science, which is great. And we did some initial scouting of the Delta before we got there with Ingenuity. So it's gone beyond its initial tech demo mission to really become trying to be integrated with the science mission. And we love that aspect of it. And certainly it means that future drones that actually have science support built into their capabilities, not just tech demo, but real science focus or engineering focus or what have you, are going to really enhance and augment future missions. So I mentioned, right, we're not just drilling, we're coring, right? We found some of these flat sort of paver style rocks, a place where we could put the drill down, get into the surface. We drilled a hole, created a nice drill tailings pile, and the bit is a coring bit, so it's got a hollow inside. So we drill it down and not just create the tailings, but capture the rock, and then pull the rock out of the ground and bring it back to the rover and put it inside a device that brings that core and into the rover and encapsulates it, hermetically seals it inside one of 42 core tube canisters that are about the size, a little bigger than a dry erase marker. So they're not that big, but they're going to be incredibly special. So our first attempt on this relatively flat lying rock, there's the hole that we drilled, there's the tailings that we created, but the core came up empty. We imaged it, took pictures of, it just came up empty. And so it must have crumbled and come out as the core bit was being pulled out of the surface. Turns out this is a pretty soft and crumbly rock. And so that was not the best stuff to sample. Too soft and crumbly, too weathered to sample, but it was sealed up. And there are two things. It's an atmospheric sample at the very least, and we wanted to collect some atmospheric samples. So we're going to make lemons out of that lemonade, right? But also, if you look carefully at the images taken of that tube, there are some little flecks and flakes, tiny chips of that rock that are still left in there. So we will get some sample. They're tiny, tiny samples, but to a geochemist, they only want nanograms of this stuff, right? And they'll tell you what the universe is made of. So we will actually get some of that sample, but it's mostly an atmospheric sample and a lesson learned about what kinds of rocks we can core into and not. It's the first time we used the coring system. So that was pretty cool. Second time.
Jim, we've got a quick question about coring. So was the method here influenced at all by the mission that landed on a comet a few years ago?
Not directly, no, but that community of folks who study how to core into planetary surfaces is a pretty small community. And so everybody learns something from everybody else. They have a very different problem, right? Almost no gravity environment that they have to try to somehow remain anchored to that surface while exerting significant force downward that, of course, wants to launch the coring system off the surface of a body with almost no gravity. So they're very different solutions, but lots of collegiality among the NASA and ESA communities who are working on those kind of problems. Great question. Okay, so we learned a little lesson. Hey, let's go find a tougher, harder rock to demonstrate the system. So here's a rock called Rochette, possibly a volcanic rock, had some textures and compositional indicators remotely that made us think, hey, maybe this is a piece of the kind of volcanic rock that you'd find in Hawaii or Iceland or northern Arizona. And let's try to demonstrate the coring system there. So the engineers found a accessible, relatively flat surface. You can see it's wind carved. It's got these flutes on its surface from billions of years of erosion by wind and sand. We first used the abrading tool. We have an abrasion bit that can scrape off that red Mars dust and get below the surface and allow us to put the microscope and high resolution imaging onto that abraded surface and look at the grains and texture of the rock without being confused by dust or surface texture, et cetera. So that's a really important tool. So, hey, you know what? This does look like a really hard, competent volcanic rock that'll survive the coring process. It won't crumble and flake out of the coring bit. And so we went ahead and tried it and drilled a hole, and core capture was confirmed. Tube was sealed. There's a nice core of this rock. There's the picture of it inside the tube. We brought the bit up to the cameras, pointed at the cameras, smile, take a picture, and then it went inside this actual core tube, which is a laboratory picture before launch. So inside that dry erase marker kind of tube is a sample of a beautiful Mars, probably volcanic rock, stored carefully in a tray inside the rover. Number one, right? Number two, if you count the atmosphere sample. And then we did another one because we like to double sample on these, because who knows if we happen to pick one place where there's something weird going on, right? Statistically, you want to sample the diversity of these materials, and that'll play into our strategy of how to cache the samples later as well. But demonstrated that this coring system really works. And the kind of cool thing is it's basically, you just give it a command. You just tell the rover, collect a core, and it just goes off and does it. It does a whole bunch of stuff, the drilling, the alignment, the transfer to the rover. There's a carousel that moves that into the body of the rover. Inside the rover, in the front third of the rover, there's a tiny little robotic arm, like a little Tyrannosaurus arm, that grabs the core and moves it from station to station, images it, measures its volume, hermetically seals it, puts it in the tray. And all of that is just, boom, you do it. It's really just a phenomenal amount of autonomy that if that hadn't been built in, it would be weeks of one-a-day contacts with the rover to verify each of these steps in the process. And instead, they decided to try to use onboard autonomy as much as possible to do all that stuff. And it's so far been working great so far. And so we've continued to do that in our drive around. And on the floor of the crater, we collected 8 core samples of both of the kinds of different materials that we identified from orbit and confirmed that they were different from the ground. And so this is really, we were able to braid each one of these samples, drill into them, capture the core, confirm core capture, do the hermetically sealing, and put it into the tray. So 8 of them captured on the ground, a great collection of rocks that are telling us about the crater floor. They're telling us about volcanism on Mars, about Mars as a planet in many different ways, not necessarily the astrobiology story, but we want to understand sort of average Mars and what is Mars composition like, what's the mantle like through these volcanic rocks. And so this is a great starting data set. Remember, we've got 42 of these tubes, right? So totally appropriate to spend 8 of them, we think, on this initial sampling activity, demonstrate the sampling system. I mentioned dust devils, right? It's been dusty times in Jezero, and occasionally these storms come along and they dump sand and dust on the rover. This was a problem for Spirit and Opportunity because they were solar powered, much less of a problem for Curiosity and Perseverance because these are nuclear powered. We use a small amount of plutonium, generates electricity, generates heat. That heat generates electricity. The electricity is used to charge the batteries every day, and then we run off that battery power. Electricity charges the batteries every night, and we run off that battery power in the daytime. So yeah, the rovers are getting filthy dirty, but it's not really much of a problem in terms of the mission. So that's been good news. So what's happening next? What's the latest going on? Of course, so we got to the Delta front, right? We finished that crater floor campaign, did that long traverse around the bad stuff, and finally got to the Delta front just a few months ago. So it's like, hooray, we're finally where we intended to be. And just like for Curiosity, the views have been spectacular. Seeing those layered rocks up close, seeing those sediments, those sedimentary rocks, sandstones, mudstones, siltstones, the kinds of things you'd see in a delta environment. There's also, the possibility that some of this is from volcanic ashfall as well. So that's a hypothesis that we're also exploring. But many of the relationships and the layers that we see to each other are just classic, what geologists call a Gilbert delta. It's a classic way that deltas form, and you see them in cross section on the Earth, and you see many of these same kinds of things. So we think, by analogy, same kind of process operating. Here's a picture just from very recently of a rock we drove up very close to, and took some up close measurements on. Beautiful layers, sandstones, and the finest ones maybe getting into the siltstone and mudstone size. So we're finally among these sediments, but at the base of them, there's this 50-meter cliff of them in front of us, but we're capturing the lowest levels of the delta where we are now. And we have just completed, just in the past week, collecting our first core samples of the delta, 2 samples from a nice flat lying rock. And here they are, pictures from Mastcam-Z up close in them. You can see that they maybe kind of look like sandstones. There's little chunks of stuff in there. There's a cementing agent here. We're capturing different parts of what might be some of the finest grain materials at the bottom of the delta, the stuff that's settled out in the shallow lake, maybe from gentle sedimentation, like I talked about before. So now we have 10 samples in the can, 10 core samples plus the atmospheric sample, right? And now we're going to start collecting more and more of these delta samples as we drive up into the delta over the next few months and years. And so that leads me to the last part here, just a few slides on what's the future, right? Well, I already kind of gave it away. Perseverance is the first part of Mars sample return, right? So our job is to collect these samples. We collect them, and we've got 42 tubes. We've got a primary mission that goes through early 2023. So we've got some more time to collect these. And then our job is going to be one of 2 things. And we don't know yet because it's all still being worked. And I invite you to go check out NASA's Mars sample return site for the latest, because it is evolving, right? Either we will deposit our sample tubes on the ground in one place or a chain of places or what have you, where they would become a cache, right? Like geocaching, right? Except it's aereo-caching. They become a cache, it's on the ground, and a future rover or other vehicle will come and pick up these sample tubes, collect them, and bring them to a lander that happens to have a rocket on it, that's designed to have a rocket on it, load those samples into the lander, and the rocket will have a capsule. That capsule launches, the rocket launches the capsule into orbit, Mars orbit, where there's an orbiter waiting that's specific job is to find and capture the capsule and bring it back to the Earth. And this is a partnership with the European Space Agency. It's possible that this part might not happen, that we might just take Perseverance itself and drive it to the lander and put the samples into the lander ourselves. We might not have this so-called fetch rover in the loop. The Europeans are playing a role in defining that. The Europeans are playing a big role in the orbiter part of this investigation. And then that sample capsule would come back in the same way that several previous NASA and Japanese and other sample capsules have come back, just by parachute into the desert in Utah in this case, and then would distribute them to laboratories around the world. And that could happen as soon as 2031. This lander and orbiter combination could get launched as soon as 2026, 2027, 2028. Okay, so that's not too far away. We're on our way to 23 now. So all the details, all the reviews, all the planning, all the budgeting, all the international collaborations that need to happen to make something like this go are being worked right now. So I wish I could tell you exactly what's going to happen. If I could talk to you in 6 months to a year, I probably can tell you what the specific plan is, but just know that right now it's a subject of intense international discussion and negotiation. And it's really exciting, right? We're working to bring these samples back. So these things that we're seeing through our cameras and through our robotic eyes, we have the chance, maybe within a decade, of seeing with our own eyes in many of our own laboratories. And that is super exciting, right? And of course, where is that leading? Where has all of this been leading, right? With sample return, getting samples back, characterizing what we know about the place. And it's not only its science and what it means for Mars history, but what it means for human exploration. What are the possible hazards in this fine glassy dust, other kind of chemicals like perchlorates or peroxides there that could erode spacesuits or what have you, right? And so sometime, I'm an optimist, sometime in the 2030s, the first crews are going to go. All right, will they be NASA crews? Will they be Chinese astronaut crews? Will they be SpaceX employees? I don't know. Will they be some of you? Potentially. I'm probably too old. I'd love to go. And I want to come back, but I'd love to go. This is, I think it's super exciting, right? And of course, haven't even talked about the moon, right? The moon is going to demonstrate some of the technologies and strategies and equipment and processes and launch vehicles and all that kind of stuff that's required to do this, but it's all focused on getting people onto Mars, hopefully in the 2030s. So that's pretty cool. And just a quick fly through summary of what's going on with Curiosity and Perseverance, just to show some pictures here in the end. This is a sunset, one of the first sunsets that we took with Spirit rover back in Goose Crater. And I was reminded of this quote from Charles Darwin in 1839, how great would be the desire in every admirer of nature to behold, if such were possible, the scenery of another planet. Well, you know what? Such is possible. We are doing it today, not with our own eyes, but with robotic avatar eyes, producing views, vistas that are no less inspiring than what we're going to see with our own eyes. Here's from Curiosity and Gale Crater. Here's from Jezero Crater with Perseverance not that long ago. And here maybe is the view in the 2030s. It's from a great little short movie called Wanderers, which I strongly encourage you to go view on the web by Eric Bernquist from Sweden. Just a wonderful little movie where he's taken many of the iconic pictures of the history of solar system exploration from Voyager and Viking and the Mars rovers, and he's put people in. He's put people in there in this hopeful and imagined future in the 2030s and beyond. And the real voyage of discovery consists not in seeing new landscapes, right, but in having new eyes. And this is where, our eyes will come into play, our own eyes, our own human eyes in these environments. So this is my last slide here. I just, invite you to follow along with what's going on with Curiosity and Mars Science Laboratory, Perseverance in the Mars 2020 mission, our Mastcam-Z investigation. We put all those helicopter movies on our Mastcam-Z blog. We put panoramas, mosaics, calibrated images out there. NASA releases the raw images every single day, right after each downlink, multiple times per day. They go out as JPEGs or PNGs in raw form to the world. There's lots of amateurs out there making mosaics and discoveries, and I think it's great. I think it's great how we're sharing all this stuff, and we want to continue to share it. So that's my update, James. Happy to take more questions, and great to sort of virtually meet all you students, and I wish you great success in your projects this summer. Sounds like a great summer for all of you.
Thank you so much, Jim. This was a wonderful presentation. Students, please feel free to turn your video on and ask a question. I know we've got a few in the chat, but feel free to take the floor first and ask a question. Anybody? I'll ask the first one, Jim. So you're probably a great person to ask, when we do plan a human mission, what would the role of rovers and drones and helicopters be to support the human crew's science operations.
Yeah, I think it's personally, I think it's critical for robotics to support human exploration. We're going to see that on the moon, over the next decade, and not just advanced scouting, but being available during these missions for scouting activities, for sample collection, for sample delivery back to the base, for to go back and grab me a screwdriver, would you? That kind of thing. So it could be as mundane as that, but it could also really help advance the pace of traverses, of scientific exploration, of sampling. So there's so many ways that robotics can augment human exploration. And I've already identified myself as an optimist. There's Bob. Bob's also an optimist, I know, right? So I'm an optimist, and I see a program where robotics and human exploration can actually move forward together and be interdependent. I don't see a problem with that. I see it as an advantage.
Okay, next question from Brian Reitkirk. He's asking, again, kind of on the same topic of a human crew. Would a first mission consider landing near Perseverance to collect the samples and maybe replenish the unused cores?
Yes, on the former. I haven't heard anything about the latter. That's a cool idea. Yeah, the sample return lander has to be not far from where Perseverance is traversing. It can be, farther away if there's a very capable fetch rover that comes along with it, or other capability to make that distance. There has to be some capability for mobility in that system, just in case Perseverance dies, before we're able to get back. So we're talking about, maybe by the end of the Perseverance's prime mission, potentially depositing one sort of contingency sample cache. And partly that's why we're taking two at every sample. Maybe we take one of each of those and put it down somewhere, and then go continue our exploration. And just in case, the rover doesn't survive, as long as we're hoping it will, there still be that cache of samples. But yes, the return lander, the return MAV, Mars Ascent Vehicle rocket, that they're going to have to be in Jezero, not far away from where Perseverance is. I am already super excited about taking the movie of watching the sample return lander come in and land with the Mastcam-Zs. That's going to be pretty cool.
Awesome. Couple questions about the helicopter. What was the original lifespan planned for it? And is there a successor planned for the helicopter?
Yeah, so the original plan was 5 tech demo flights early in Perseverance's mission. So sort of, within that first 3 to 6 month period. And so when those were done and successful, highly successful, and we've got movies of all of them, and the helicopter's still in great shape, then JPL and NASA headquarters had to negotiate an extended mission for the helicopter, just like we have to negotiate extended missions for other missions that are still doing well and still capable of doing great additional science. And so they negotiated an operational demo phase for Ingenuity, where it would do a lot of that imaging, go to places where the rover couldn't go, but what the science team wanted that information at a much better scale than you can get from MRO, from orbit, higher resolution. And so the science team has been, suggesting ideas and flight paths and working with the helicopter team at some level to do that ever since. And that's the phase of the mission that we're still in, that operational demonstration, again, a demonstration phase. And in terms of follow on, I don't know exactly what's going to happen, but the capability has clearly been demonstrated. So I know JPL has plans, of course. APL, Johns Hopkins are planning to fly a quadcopter on Titan, right, in the 2030s, right? And some of the lessons learned from Ingenuity are going to go into that, and back and forth. Again, it's a small community doing this kind of cutting edge robotics, interplanetary robotics. And so I think that there is a place for these kinds of drones in planetary exploration for planets with atmospheres.
Sounds good. Yeah, and they got a little bit of a preview of the Dragonfly mission from another lecturer.
Good.
Great. Well, thank you so much for taking
Wait,
time out of
before
your
he
day to
goes, I
talk
have
to
a
us.
question for him.
Oh, yeah,
Oh,
go ahead,
Bob has a
Robert.
question. Sure.
Yeah, Jim, the students here are going to do designs of human Mars exploration mission. And as part of that, each team is going to choose the place where it's going to go. And then set science priorities accordingly and equipment choices accordingly and all the rest of that. Now, I don't know that, because I haven't attended all the lectures in this series, but can you recommend a book or other reference that the students can go to that describes the different places on Mars? In other words, where they can look through that and see, you know, here's this one, which has got these characteristics, and that one with those characteristics. In other words, a reference that they can use to help them choose their destination.
Oh my gosh, there's many, and almost all of it is online, publicly available from every one of these Mars landing site selection workshops that have been held for Pathfinder, Spirit, Opportunity, Curiosity, and Perseverance. 5 different sets of international workshops held, each of them over 2 to 3 years, all of which, all of the proceedings, all of the reports, all of the individual presentations are all online.
All right, but is there any book that would be accessible that might be comprehensive? Because, for instance, some of these rover missions, the pole was off, it wasn't part of the selection. Right. Other places weren't part of the selection. You know, where you could really, I think Bill Hartman had a book a number of years ago that was a traveler's guide to Mars. Maybe there's something better than that you could.
You know what? I don't think there is a single source. I really don't. I think reading the reports from each of those landing site workshops and the introductory material, I think is approachable. I mean, there was public participation.
Well, could you then do this?
Some of those.
Could you send Jim Burke some links to some of the more appropriate reports, and then he can post them as a resource for the students?
Sure, although I bet a number of students out there have already found them just from me saying Mars landing site workshop, and they've Googled it. They're probably already on 5 of those sites already, but I'm happy to do that. Okay. I've written some things. Bill Sheehan and I have a book that just came out last year called Discovering Mars, which is a history of the entire exploration of Mars going back to the Babylonians. And I talk about landing site selection in there, and there's notes, extensive notes and references in the back. I wrote a fun, light book called The Ultimate Interplanetary Travel Guide a few years ago, where I talk about landing sites on Mars and the process. Again, it's public. It's not a scientific book. It's meant to be fun, like a travel guide.
Sure.
But that also, I talk about the process. You can read, there's parts of Steve Squire's Roving Mars book about Spirit and Opportunity that get into the landing site selection process at kind of a technical level, but for students who've taken some geology or have a little bit of a deeper engineering background already, I think some of that could be approachable. Okay. And then I wrote a book back in 2006 called Postcards from Mars, which was also the title of the talk here, which is intended for the public, not high technical detail, but that goes into a bunch of detail about the Spirit and Opportunity landing site selection process, right, along with some links and references. Right.
But also,
I'd be happy to kind of package that up.
Link, that sort of talks about all the different places, because rather than the process of how this committee down selected to that.
Yeah, I mean, and there's Phil Stook has an atlas of Mars that's just wonderful, right? And maybe you've seen, okay. He's a Canadian planetary scientist, Stooke. That's just beautiful resource. It's a little bit out of date already because of what MRO has done with HiRISE, but that's a great resource as well. But you know what? There's no single place. There's your next book project, future author out there.
Okay, well, thank you.
Awesome. Thank you so much, Jim.
Great. I'm going to drop off. Great seeing you guys. I think I'll see you in the fall at ASU.
Yeah,
yes,
absolutely.
Society Conference. I'm looking forward to that, and we'll get together and share more stories and details.
Awesome. Thank you so much.
All right, I'm going to stop sharing and then drop off here.
Okay, all right. Our next
Thank
speaker
you.
then, so we'd like to welcome back Robert Zubrin, and he's going to talk a bit more about our competition and the ground rules for that and some other topics. Go ahead, Robert.
Okay, so now you all have had a couple of weeks of lectures on the different aspects of Mars exploration. And I hope you've done some background reading. I recommended 2 chapters from my own book. You just heard Jim Bell, and he's got a couple of works that could help you choose your landing site and also perhaps your science priorities. But this is where we now switch gears because the course so far has been somewhat conventional in that it's been teachers talking to you. But now you are going to have to talk to each other, and you are going to have to start generating original ideas. You've heard from us. Now you got to hear from each other and start thinking. So you're going to be divided into 6 teams, each with roughly 6 people in them. There's going to be, and it's more or less divided by time zone, because it's much easier to collaborate with people who are in your own time zone than people who are on the other side of the world. So we have an Asian group, we have a European and Middle East Africa group. You're not all in exactly the same time zone, but you're only a couple of hours apart from each other. And then in North America, we have 4 groups, including 1 from the West Coast, 1 from the Central Time Zone, and 1 from the 2 from the East Coast. So those are in the Americas. And they include not just people from the United States, but from Canada and Peru and perhaps other Western Hemispheric countries. But you're now going to have to try to design a Mars mission. Now, this is how it's going to be. You're going to get 30 points for the scientific merit of your mission, 30 points for the engineering technical credibility of your designs, 30 points for the human factors and life support considerations. That is, you have to keep, you have to choose the right crew. You have to keep them in a reasonably comfortable situation so their morale does not fall apart while they're trying to do the science. And you have to have maintain sufficient life support for them. So there's that. So it's 30, 30, 30. And then there's 10 for cost, which figures into everything. And if this was the design of the full mission, that included the launch system and the interplanetary transportation, the ascent vehicles, and all other things, cost would be bigger than 10% of the consideration. But since most of the cost of the mission actually is in those other systems, the cost here is a more secondary consideration to what you're actually delivering within the 30 tons that you have to work with. Okay, now again, I believe that we have a maximum crew size of 6. If that's correct, Jim?
You said 5 last time?
Did I say 5? Maximum crew size of 5. And the maximum stay is on the surface is a year and a half. So that is a total of 7.5 person years on Mars. So that would give you the maximum punch in terms of human abilities and person days on Mars But if you want to do that, then you have to have supplies and life support to accommodate that. And that will require mass. And if you and that will take away from mass that's available for scientific equipment, vehicles, other things. But there it is. You can maximize your human capability, or you could shorten the stay. You'd need less supplies, or you could reduce the number of people, which means you'll have less skills. Now, I just want to check on that again, Jim, on the actual solicitation that we put out in the when we opened the invitations for the class, we said 5, not 6.
I don't think in the original announcement we mentioned the crew size. Let me double check that. Yeah, it doesn't say anything about that.
So it was just me talking. Okay, in that case, I misspoke. Let's make it 6 is your maximum crew size. But 1.5 years is your maximum stay time, okay, on the surface. So you could have 6 people times 1.5 years is 9 man-years total of activity on the surface. Or you could go with a shorter stay or a shorter crew. You have to choose where you're going, okay? And so Jim just gave you some references that you can use to help you make your selection, okay? And again, the purpose of the mission is to accomplish the most science possible. And so you're going to have to choose what is the most relevant science. Is it hunting for extant life? Is it hunting for fossils of past life? Is it geological exploration? What other kinds of questions are there to investigate? And if so, okay, you have to choose the site that is geared towards that. And then you have to choose equipment that is relevant to that site. For example, if the site is a plane that is, you could say, if you wanted to drive over in a car, if it's that level and obstacle free, then you might want to have a pressurized rover that will allow you to travel very long distances across that kind of terrain. On the other hand, if it's a bunch of boulders of a foot or two in diameter, a car won't work there. Maybe an all-terrain vehicle could travel across it. Or maybe you have to think about flight systems. What would it take to have a helicopter that could transport your crew? Or other kinds of things. Or you're not limited, by the way, to devices that have been already demonstrated. For example, the Ingenuity was a helicopter, but one could imagine a tilt rotor airplane, which can take off and land like a helicopter, but then has wings. And with wings, you can travel a lot further with a given amount of energy stored in your batteries or whatever than you can with a straight helicopter. Airplanes can fly a lot farther than helicopters can fly. But then you'd have to introduce that. Depending upon what kind of science you want to do, there are different kinds of instruments that you're going to want to bring. Some of these instruments may be instruments that the astronauts carry around with them. Others may be instruments that are in a laboratory in your habitat spacecraft, so that they would bring the samples back there and be looked over in instruments there. And obviously, you probably want both kinds of instruments depending upon what you're looking at. But you need to make an instrument selection. You need to make a crew selection based on your science objectives. Also, you're free to choose the other characteristics of the crew in terms of Do you want an international crew, or all from one country, or from two countries? Do you want to have men and women both, or more of one than the other, or all of one and none of the other? What kind of age distribution do you want this? What, and most importantly, the skills. Okay, who should be in this crew? Now, here's the thing: you have scientific tasks to do, but you've got a lot of equipment on this mission, and if it should fail, that would cripple the science and possibly endanger the lives of the crew. So you need to, you'll need to have engineers, mechanics in this crew. Okay. Do you have a doctor in the crew in case someone gets sick? Or with 6 crew slots, do you have someone whose primary assignment is, say, to do field biology, and there's only secondarily a doctor? Or do you want to have someone who is primarily a doctor? And if so, now you say, well, field science is what it's all about. You know, do you have one field scientist in the crew? And if so, what is his or her specialty? 2, what are their specialties? 3, you know, describe the crew members. And maybe you can describe crew members who have multiple skills. You know, I mean, there are doctors whose hobby is race cars, and so they're both an auto mechanic and a doctor. You know, this is kind of thing. What kind of vehicles, again, do you want? That can be terrain dependent. So, you know, are you going to use single person all-terrain vehicles, 2-person all-terrain vehicles, pressurized rovers, that is, say, cars about the size of SUVs that have a pressurized environment, or maybe something, a mobile lab the size of a recreational vehicle, the size of a school bus. So you can, the whole crew can travel around with all their equipment. The utility of such large vehicles does depend upon the trafficability of the land in the region that you're selecting for your mission. Okay, aerial vehicles are cool, but what size? You know, little ingenuity can carry a camera. A bigger helicopter might be able to have a camera and a number of different instruments, or you could have a much bigger helicopter and the crew can travel in it. Now, again, you're not limited to things that has already been demonstrated. Obviously, nobody could do a human Mars mission with things that have already been demonstrated, because no one has done a human Mars mission. But you want to be credible in the technology that you are projecting. Okay, it's one thing to project a tilt rotor aircraft. It's another thing to project a teleportation system. You know, one is a matter of engineering, so a helicopter with a wing and the propeller turns and tilts. Another is something invoking physics that we don't have. So now you say, what about something in between? Fusion reactor. Well, fusion reactors are possible. We don't have them yet. You could invoke that, or you could stick closer to what we have and go with a nuclear fission reactor, if that's your power source. If you want to look for extant life, you might want to drill. But in that case, you need to take drilling rigs and something to power it. Well, if you're just drilling right at the base where you land, then you can use the base power source that you have. If you want to drill in lots of places far apart, you need to have power at a remote place. Well, how are you going to do that? You could haul around a nuclear reactor. You could haul around a bunch of solar panels. You could make chemical fuel with, you know, as described in my book, The Mars Direct. You can make methane and oxygen and take them and use them to generate power far away from the base. There are other things that you can do. So you can invoke technologies, and that we don't yet have, but the further out they are, well, they may be more capable, but they'll be less credible. So it's up to you to choose technologies that are good enough to do the job, but credible enough that someone could say, hey, we could plan a mission with this. And by the way, we're thinking about this mission happening in the early 2030s. Okay, so this mission is landing on Mars no later than 2033. And so you can imagine a bit as to what kind of things might be available in the world 10 years from now. Okay, it could be that, you know, okay, the kind of mobile robots we have now are things that are either like wheeled rovers or rovers with treads like tanks or helicopters, but perhaps it's not too much to think about rovers that can move around on legs, and you know, a dog can run over a boulder field much better than you know, a wheeled vehicle can, and a cat can climb things, and maybe there are robots that are designed with mobility systems comparable to those that would allow you to travel over rough terrain, at least with the rovers, or maybe with vehicles with such legged mobility systems. You can use your imagination here. You know, 10 years, new stuff can be built in 10 years. So you can invoke new stuff, but don't get too wild or you'll get marked down as not being credible from an engineering point of view. Okay, that's the trade between new systems with novel capabilities and but the more radical they are, the less credible they are. Okay, so you're going to have to go a bit beyond what people have now, because we don't have enough now to do this mission. We also, by the way, in the human side of this, you need to design spacesuits for your astronauts that give them the ability to do field exploration. So, you know, like the kind of spacesuits that NASA uses on orbit now, which, you know, are clanky, heavy things that you couldn't use them on the surface of a planet. If you look at the suits they used during the Apollo program to travel on the moon, they were much more flexible. But maybe you could come up with something better than that. There are, you know, there's pressurized spacesuits like the Apollo suits and our current suits, but some people talk about using elastic spacesuits to exert the pressure on the astronaut, and that would make, you know, then they're like skin type spacesuits. Yeah, well, Larry Kuznets sometimes talks about them. Dava Newman from MIT. Dava Newman is a scientist at MIT, and she's done a lot of work on elastic spacesuits. So maybe that's a way to go. You know, you want to design your habitat, and you know, depending upon, if you go with a crew of 6, the habitat's got to be designed for crew of 6. You're going with crew of 4, it can be designed for crew of 4. You know, but
I just put in a link. There's a TED Talk by Dr. Devin Newman about spacesuit design.
Right. Okay. So there's that kind of thing. Then you're going to need power for the base. Okay. You need power for life support, but you may need power for more than that. For instance, if you're using electric vehicles, you're going to need to recharge them. Electric helicopters need to be recharged. If you're going to make propellant to use chemical fuels for any purpose, including vehicles or drilling rigs or things, then you're going to need power to make chemical fuels. Then you've got life support systems. Are you going to bring your food? Or are you going to grow your food? Okay. If you're only staying for a month, there's no point growing your food. Okay. If you're staying for a year and a half, you might want to consider growing some of your food. But then you want to look at what kind of crops can you grow in a short period of time in a greenhouse of limited size. And if you do bring a greenhouse, you're going to have to calculate its weight and the weight of the systems that it needs, the pumps and all that. If you are bringing your food, you got to calculate the amount of food. Now, there are foods, you can eat apples and oranges, but most of them are water, and you can recycle water to some extent. There are various literatures out there about people claiming to be able to recycle 80%, 90%, 95%, 99%. I personally think 90% water recycling is credible, but that means that means if a person uses a total of, say, 30 kilograms of water in a day, that they're wasting 3 because they're recycling 90%. But if you do that, if you recycle the water, then you got to account for the weight and power of the recycling system. Okay, now that's probably going to pay off because people use a lot of water, and that is pay off in terms of weight. But then food, well, as I say, some foods are mostly water, and maybe they can be brought in powdered form and you could add water to them. Pasta and rice and flour used to make bread in their dried form are much lighter weight than the product that you get. Okay, but then there's other kinds of things. So what is the diet of the astronauts going to be, and how will you meet it? Now, you can even get water from Mars if you go to a place where water is known to be. Because if you go to a place where there's water ice. Now, if you do go for using Martian ice, you've got to have to bring the equipment to extract water from the ice. Okay. Now, in Antarctica, for example, where they do get the water for the Antarctica base from ice, the way they do it is they have this system that pumps hot water down into the ice, and it melts some ice and it comes back as cold water, but there's more of the cold water than the hot water you pump down. And so what you basically you keep cycling down more hot water. So it takes energy to do that. You got to heat the water and pump it, but you get water that way if you're in a place where there's ice. If there isn't ice, another technique that there are some places on Mars where there isn't ice, but the soil is over 50% water by weight. It's like frozen mud. You could bake water out of that soil. Even 10% water, you could bake water out of it. But then you got to look at the energy involved. Okay, so there's all these things that feed into it. Then finally, there's cost. Now, the cost is, in this case, is going to be notional, because there's no way you're going to be able to get a list price for a Martian helicopter. You can't order these things out of a catalog, but it's going to be somewhat subjective. That is, for example, if your mission plan requires little helicopters, mid-size instrumented helicopters, human transportation helicopters, pressurized all-terrain vehicles, and ATVs, it's going to be more expensive than one that just requires ATVs and little helicopters. That is, the more different things you bring into the plan, the more cost there's going to be. The main cost in aerospace systems of this kind is not the cost of the machine itself, but the cost of developing it. So you're going to have to do a certain amount of development to make your mission possible. But you just need to understand that while the more different kinds of equipment you can bring to Mars, the more capable you're going to be, the more it's going to cost. So you don't want to get too crazy. You can get, in other words, you can get a lot of what you want, but you can't get everything you want. Okay, you're going to have to basically say, let's try to slim this down a bit. Okay, we've now, we have a list of all the things we'd like, but how much of this can we drop and not lose a significant amount of our capability. Okay, so that's how it is. So now each of your teams has got 6 people, or I think there may be one with 7 or so.
Yeah.
Okay, you want to divide up into 3 groups, each with at least 2 people: a science group, an engineering group, and a human capabilities group. Okay. In a certain way, the science group drives the mission because they choose the site and they choose the objectives. Okay. That then means the engineering people are going to have to come up with the best kind of equipment for that site that can meet those objectives. Now, it's not like the science group can just dictate, because if they say, something like, we want to do our mission underneath the ice cap, or you say, how are we going to get there? Okay, there can be feedback from the other groups of, look, that's just too hard. But if they choose, but for the most part, if they choose an objective that is reachable, then the other people have to play along and say, okay, we the engineers are going to design the systems to make this happen and happen in the best possible way. And then the human capabilities group is going to have to choose the right kind of crew for that mission, the size of the crew. If you're going to a place where there is water, it might be easier to have a larger crew with full duration, because part of your life support's right there. But the human capabilities, they are going to make the specification for the habitat as well. So they're going to be architects. Now the engineering group is going to have to engineer that, but say we want to make this thing. You can make it as the rigid structure as much as 8 meters in diameter. If you wish to use inflatables, you can invoke bigger structures, more roomy. But now you've got an inflatable to deal with, and you have to engineer that. And you have to engineer in a way that when you go in and out of it, it doesn't deflate when you open the door, this kind of thing. So the engineering group's got a lot cut out for it, because basically the science group and the human factors group are there to say, this is what we want. And the engineering group is there to say, well, this is what you can get. And you want to have them be able to get as much as they can of what they want. But, in life, you always want more than you can get. And that's certainly very true of this sort of thing. And then you're going to have to figure out how much all this weighs. And you have a mass budget, 30 metric tons. That's 30,000 kilograms. Okay, so we're not talking about English tons, 2,000 pounds. We're talking metric tons. Metric ton is 1,000 kilograms. So 30 metric tons is 30,000 kilograms. That's the total useful mass you can land. You don't need to account for the mass of the lander itself, as the platform, for instance, that delivers your hab to the ground. But you have to account for everything that's on it. Okay, and that includes the habitat, its life support systems, its supplies, all the instruments that are either in it or will be used in the field by the crew, all the vehicles, whether they are ground or air vehicles, and then the crew and their consumables as well. So this is pretty intense to try to figure out all this. And you got to do it with 30 tons. And you might want to, this is always very good practice in aerospace, have some margin in which you say, we can do this in 28 tons. But if we're wrong by a little bit about how much things are going to weigh, we've got an extra 2 tons. Or you could say, well, we're designing all this and we're filling out the 30 tons. But if things are overweight, we can get rid of these 3 things, which total 3 tons, and we can still do our mission without them. We can down select, as it were, and basically say, okay, we can't bring the extra suitcase. And we're still doing the mission. It's just we don't have the extra thing. Now, also, you have to think about things like this. Let's say you're going with all-terrain vehicles. And you say, well, I got a crew of 6, but I'm not going to send them all out on all-terrain vehicles at the same time. So maybe I don't need 6 of them. Maybe I can get by with 3. But what if one of those breaks down? You know, what's your degree of redundancy, the degree to which you can fall back? Okay, so there's all these things. Okay, so to try to take into account, how many of these do we bring, and what's our I would think the minimum for useful activity would be 2, because you don't want to send astronauts out alone on long distance treks. Now, how far can you go from the base? Well, further the better. If you have a helicopter, you can go very far. But is the helicopter going to be pressurized? In which case it's heavier and bigger and needs a lot more oomph to get it flying. Or is it going to be unpressurized? You travel in your spacesuit. Well, if you travel in your spacesuit, you know, you can be out for the day, but it's a day trip. You got to go back. But there you go. You could have a pressurized rover, or maybe you have a pressurized trailer that ATVs can either take with them if you want to do an overnight trip away from the base, and you can live in the pressurized trailer overnight, but if you don't need it, they can detach from it and go zipping around without the extra load. These are all ideas to think about. And it's for you to design. So you're going to want to put 2 people at least on each of these 3 principal groups. And then each group should try to exercise some discipline in controlling its costs. And as I say, cost in this case is really development costs for all the different kinds of things you want to bring into the game. And you may need to negotiate a bit, you know, you may need to say, look, if we want to have 6 ATVs, we have to have less science equipment. Or if we want to have our life support system in the hab sufficiently backed up, we can't have 6 ATVs. How are you going to do this? So you want to try to design this as best you can. All right. So next week, you should also choose a team captain, okay, to coordinate your efforts. And this should be someone you trust to stay on top of things. And you're going to have to figure out a process for adjudicating disputes, because if the life support people, human capabilities people are demanding more mass for their stuff, and the scientists want more equipment, someone's going to have to decide. Okay, and you can either have the captain decide, or you can have it decided by a group vote, with maybe the captain getting 2 votes to break the tie, if you have a group that has got an even number of people in it. But some way to resolve disputes, because there will be disputes. There will be different ideas on how things should be done, and there'll be different ideas on how things should be prioritized. So you're going to need to be talking to each other. First of all, you're going to need to talk to your teammate within your group. Then the groups need to talk to each other. I would suggest you hold, okay, next week you're going to do this. You hold a design review on next Friday to review what everyone has come up with, and try to, well, first of all, you want your science team to decide on a site relatively quickly. Okay, you may want to choose who's in which team today. You have each other's names and emails. Maybe you have a group meeting today and figure out who's going to be in the human capabilities group, who in the science group, who in this. And then get on it. The sooner you can figure out where you're going, the sooner people can be designing stuff. A certain amount of design you can do that is regardless of where you go, HAB, for example. But you're going to have to figure this out. Are you bringing a nuclear reactor? Are you going to try to do solar power? All these things. But decide where you're going to go quickly, then have the groups be designing away, and have a group review no later than next Friday. And don't be afraid to be critical of the ideas that another group has. Someone says, we're going to do it this way. You say, that never work. Think about this, okay. And then you're going to need to come to a dispute whether it's a good idea or not. And if it's not, then they have to come up with something that will work. Okay. So you're going to have 2 weeks to do this. Is it 2?
I think we said 3, right?
3. Okay.
Yeah.
You're going to have 3 weeks to do this process. Okay. And then each group will have a coach, which will try to help you along to help this process and help you get it done. They're not there to tell you the answers. They may tell you where you might look for answers, okay, or data, okay. And for instance, today I asked Jim Bell to provide you with references on all the different places on Mars, and which are interested for which type of research, which would be best for looking for extant life, which would be best for fossil hunting, which would be best for geology. So you got 3 weeks. So you should definitely have a preliminary review at the end of your first week to get all your thoughts together. The people from the different groups present to the whole group. This is what we've come up with so far. Here's our idea. And other people say, well, I like this, I don't like this. You're using this big inflatable HAB. This is really cool, or this looks stupid, or whatever. And here's our concept for a pressurized rover that could travel over any terrain, because of its design, so that we can bring the capabilities of a field lab together with full mobility. All this kind of thing. Then you're going to want to have, then you get to work. And now you don't want to only talk to each other at the reviews. You want to be talking to each other. You may want to have even a daily brief meeting to discuss, well, here's what we came up with so far. This is what we're working on right now. But then, a show and tell by each of the 3 groups to the whole group, to the whole team at the end of each week. But then, so that goes on for 2 weeks. Then in the 3rd week of this, you're going to want to be writing this up, okay? And you want to make a design report, okay? And the design report can be no longer than 25 pages. I'm telling you the format right now, no more than 25 pages. Use 12-point times type style. And it can be, you can have illustrations, and these can either be publicly available illustrations that you take off the net, or you can draw your own. In the case of original designs, you'll have to draw your own. That's cool.
We've got a question, Maximus. Do you want to go ahead and ask your question?
Could we set up like a Discord group chat so it's easier to communicate?
Yes, we already have you guys in Discord, and you can feel free to use that or set up your own. You really can use whatever tools you're comfortable with working together.
Right.
Thank you.
You could set up Zoom calls among your group. Okay. So in the 3rd week, you're going to be writing up your design, okay? And, you know, this total 25 pages. You can list some references, but the references don't have to fit in the 25 pages, but the list does. Okay, so that's within the 25 pages is the list of references. So you can use illustrations, either publicly available or those you create yourself. Now, 25 doesn't divide evenly by 3, and nor does it even have to be approximately even. You may have, you know, 5 pages on science and 5 pages on human systems and 15 pages of engineering, or it may be the other way around. Now, once again, what I have generally found in this sort of thing is that when there's a page limit, you're over it, and somebody is going to have to cut it a bit shorter. You know, you may say, look, you know, sorry guys, you don't get 20 pages for your section. We're giving you 12. Okay, so figure out how to say what you got to say in a shorter way. There it is. Okay, so then that's the third week is the write-up. And then you'll also, you know, writing that up, you want to review what the other people in your group have written and challenge it. Say, look, you haven't explained this adequately, or what you're saying here makes no sense, or I really like what you're saying. It's great. And you try to put it together so that by the end of the third week, you have a design report. Okay. Then in the fourth week, okay, here's what we're going to do. Okay, first of all, each team is going to have a half hour to do the presentations in front of a set of judges. Okay. Then each team will have a half hour to make criticisms of the other team's designs. Not a half hour. In other words, if you're on team number 3, you don't get a half hour each for 1, 2, 4, 5, and 6. You get a half hour to badmouth all the others. So you might only want to spend 5 minutes on team 1 and none time on team 2 and really destroy team 4. Okay, but okay, so you're going to you're going to be able to make criticisms. Okay, and then in the final round, you'll each have a half hour to answer the criticisms that have been made. Okay, because let me tell you, in competitions, engineering is cutthroat, and people are promoting their own concepts and they're cutting down other people. Okay, now this you don't want to. It's not personal. You know, it's not. You know, so and so came. You know, looked really stupid giving his talk. No, it's they said they would do it this way. This is not credible. It won't work. You know, and their design is defective for these reasons. Okay. And then you can answer, no, you're wrong. It will work. Here's why it's going to work. You don't understand. So there's a bit of an engineering debate. Okay, this will all take place on Zoom in front of the judges. Okay, and then the judges will judge, and we will award points up to 100 points to each team based on the scoring system that 30 for the scientific merit of the mission, 30 for its engineering credibility, 30 for how well it deals with the issue of maximizing human capabilities, and 10 for cost. May the best team win. And then we will, it's our intention to collect the designs. People will have an opportunity to correct their design reports, and then we'll publish them as a Kindle book, Designs for Human Mars Missions. I'll write a preface and we'll have the design report of each of the 6 groups in the book. And I think it'll be good because what you're doing here is not just an exercise. It's important because NASA and even SpaceX are devoting all their thinking about how to fly to Mars and how to fly back. They're devoting very little thinking about what they're going to do once they're there. But that's what the mission is actually all about. The mission is not about saying you've been to Mars. The issue is about what you do when you're there. And there's no point going to Mars unless you can do something effective when you get there. So that is what you are being asked to think about. That's why we've excluded designs of the flight systems from this design project. We're just interested in what do you do once you are there. So I'd be delighted to take questions if there are more questions.
Students, feel free to unmute and ask any questions you have. Anyone?
Yes, sir.
Go ahead,
Given that how the landings work, could it be possible that you could land stuff in advance and have or repurpose rovers that have already been landed on Mars as
You
sort
can
of
land stuff in advance, but it all has to be within 30 tons. You've got a
Okay.
30 tons delivered to Mars budget. And you could land some of it before you land the crew and take time to deploy something before you have people on the surface. But you've got 30 tons. And whether it was all landed on the same day or part of it was landed 2 years in advance, that's up to you. But 30 tons is what you've got.
Thank you, sir.
Any other questions?
Someone asked how many points are in total. It's 100.
Is the judging for the paper and presentations separate?
No, they are combined. There'll be the written, in other words, you should have your report divided into 3 sections, 4 sections. 3 it can be, which is the 3 major fields that we discussed. And within those, you can make points for yourself. That is argumentative points on, well, we've designed to minimize cost of the science equipment by using the same thing to do this, is to do that, and that kind of stuff. But it's basically, you want to have 3 sections in your report and 3 main sections in your presentation. Okay, but the point is to do science, to be able to do the science, and to live through it. So science, engineering, and human capabilities.
Are points awarded on the level of detail as well?
Well, the level of credibility, you need to explain it enough to make it believable. And, if you have a very detailed science program, to the extent that you have really clarified, this is what we're going to do in month 1. In other words, the science program, is not just we're going here and we're going to look for fossils. You might say in month 1, we're going here, we're going to map out the terrain, and then in month 2, we will actually study terrain grid coordinates, 1 through 8, and then month B here, and then having done a preliminary survey of each of the 8 terrain areas, we're going to decide to focus on the best one, and then we're going to set up drilling rigs. You can outline a program of exploration. The more thinking that you evidence, yes, the better.
Do we get extra points for leaving supplies for future missions?
That's an interesting question. You certainly get extra points for finding out things that will be of value to future missions. If the stuff is potentially reusable by future missions, that does make it a better thing than something that's going to be destroyed when you leave it behind. But to my mind, early Mars exploration missions, I mean, people disagree with me on this. There are people who would want to send all the missions to the same place and build up a base. I think early Mars missions, the first one should go here and the second one should go there, because there's a lot of different kinds of places to explore on Mars. So really, the grading is based on what you accomplish, how much an exploration you accomplish in the region where you are. Now, in the course of doing this exploration, if you find out things that will be useful for people who are going to explore elsewhere, that definitely is useful. But the idea that, you know, we're leaving behind 200 kilograms of food, no, I'm not going to give you credit for that. Might give you credit for having margin on the amount of food that you would need for your mission, that you played it safe, that you had extra amounts of, well, food, and, you know, so that if the return launch was delayed or something, or certainly extra equipment to replace things that break down, that's all good. But basically, you're being graded on what your mission accomplishes.
There's a question on return fuel for the return flight. Remember that you don't have to worry about transportation at all, right, Robert?
That's right.
So there's a fully fueled Earth return vehicle for the crew.
Right.
You don't have to worry about bringing that with you.
Okay, it's not your deposit.
Yeah. Can the lander support the crew for a few days as they set up their Mars base and habitat?
Sure, if you design it right, of course.
Any other questions? Is the written proposal scored before the presentations, or will the debates sway the scoring to some extent?
The debates will sway it.
Yeah, I think we're judging it all in totality, basically.
Yeah, it all gets factored in, but you've got, in other words, look, you're making your case with your written report and your presentation, okay? Then people will have a chance to criticize it, and you'll have a chance to play defense, okay? And then, having considered that, considered what you said in the first place, how true or false these criticisms may be, and how well you came out of the criticism, how well you were able to answer it. In other words, how defensible is your mission after people have had a chance to knock it a bit? And then that's how you're graded. Now, if there is something wrong with your design that someone points out, you will have a chance to correct that before we take your report to the publication. Okay, so if there is a valid flaw in it and that you can fix by changing something, you'll have a chance to do that.
Will the presentation be done by everyone in our group, or will one person present?
That's for you to decide. If it turns out that you've got somebody in your group who's really good at doing presentation, you could have her give the whole talk. Okay. If, on the other hand, you think you've got all 6 of you should be up there and take turns giving the presentation, or maybe one from each of the 3 subgroups, how you do the presentation is up to you.
Question is, we need to design the lander and landing procedure, right? The answer is no, right, Robert?
No, no, you're not into the lander. Oh, I see what the question, the person said, if I'm in a separate lander. I was assuming that people were landing in a habitat craft. Okay, now you can have more than one craft landing. Okay, in other words, so long as you fit in 30 tons, you can do this any way you like. So you can have more than one lander. You could have 3 landers, each of which are landing 10 tons. Okay, if that works out for you. Okay, but the one of the things that is landing is, well, the primary habitation. And if you want, you could have more than one habitation. You may argue that that's good for redundancy, or that everybody doesn't have to live together, or maybe it's better that everyone does live together, so there's somebody to talk to. But the lander, which is to say a propulsion stage with a platform on which things can be placed, that is not your design. Okay, whereas you've got these flying carpets that come down and land on Mars, and it's for you to design what's on top of them. Okay, so you could have, you could have this all be in one 3-deck habitat, with the vehicles in the lowest deck and some other stuff in the middle deck and the habitation in the highest deck. Or you could have 2 2-deck habitats or 3 1-deck habitats, that have different purposes, but you've got a total of 30 tons of mass, and the habitats, rigid habitats, can only be at most 8 meters in diameter, although you can have inflatables to expand it.
Any other questions? Can we have 2 landers land at the same time?
Yes. Now, you have to come up with some reasonable distance between the landers when you're landing them. You can't have 2 landers landing at the same time that are 1 meter apart. You can, if you make provision to move things once they're on the surface. You just have to have a design for how to do that. Or you could land them, 50 meters apart and create inflatable tunnels between them, or things like that, or have a shuttle car that is pressurized that goes from one to the other. Okay, or the way I think of it, realistically, I think you only want to have, well, I'd be giving away answers if I say this, but not all the landers need to be pressurized. Okay, whereas you have to have at least one pressurized lander for people to live in. Others can just be unpressurized, but they contain the vehicles and other things, and you just open the door and you wheel them out. You can assume that the landers, that the landing platform on the landers is 2 meters above ground level, so that you would extend a ramp from them to walk down or drive down out of the lander onto the ground.
So
They are
the 25,
1 meter above ground. Okay.
Does the 25-page limit include extra information like appendices? I think you said that they
Yeah,
could.
it does. You can have a
included.
list of references. The list of references is within the 25 pages, but the references themselves can be much more than 25 pages. However, you're going to be judged primarily on what someone can read there in the report and on what you present. Now, if someone criticizes your system as saying, you know, this won't work, this is a stupid life support system that's just not going to work, and you have a reference that shows that it will, in your rebuttal, you can bring it up, say, here's reference 1. This was done at Los Alamos, and this showed a study, and we're basing our numbers on that. Okay, you know, say.
So a couple more questions on landers. Does the 30-ton limit include the mass of the lander itself?
Once again, it does not include, if by lander you mean the landing platform with its engines and tanks, no. It only includes the thing, in other words, the lander is a flying carpet. It's what's on the carpet. That's your mass.
So do we just assume a landing vehicle is landing with our supplies and resources with viable fuel and mechanics for sustaining a descent, not contributing to our total weight limit? The answer is yes.
The things that are being landed are included in your weight. The landing system itself, including its propellant, engines, and tanks, is not included. Okay? It's, you know, you're the packages in the back of the pickup truck. They can weigh 30 tons. We're not counting the truck.
Right. Any other questions?
Can the astronauts build a part of the habitat?
Out of local materials?
Or one's brought?
Yes, but they would have to have some place to live in before it's built. But for example, you could have the basic habitation in the rigid lander, and then you could have an inflatable that is deployed out on the surface and inflated and fitted out over the next couple of days to give them bigger living areas. So they can have an initial living area in their habitat that is landed, and then they can build by whatever means expanded living space.
Thank you.
Okay, any other questions? Okay, I think we got them all in.
Okay.
So students, just to, oh, there's one. There could be substantial synergies with the return vehicle, energy supply, fuel production, storage, bringing down the mission weight. So again, you don't have to worry about the return vehicle for the crew. That's already on the surface.
Right. No, I understand that the question has some validity because, for instance, if the return vehicle was being fueled by in situ resource utilization, there would be a power supply near it. But I am assuming, but what if you landed 2 kilometers away from the return vehicle? Its power source would not be available for your base. So, and then of course there are mission scenarios where the ascent vehicle does not use in situ propellant. I'm leaving that one off the table. I'm requiring you to bring a power supply sufficient for your base's needs, and for such propellant making as you need to support your operations, but not to fuel an Earth return vehicle. So if you're going to use, you could use, I mean, it's conceivable to use a rocket vehicle, to a rocket hopper to travel long distances on Mars and come back to the base. And if you want to do that, you would need in situ propellant production capability on the scale required for that. Or you could use airplanes or helicopters that either use rocket propellant or combustion engines, or drilling equipment that uses combustion engines, in which case you would need ISRU for that. But that's still, all that's going to be on a lower scale than is what's required for Earth return vehicle. And so it's up to you if you want to do that.
Okay, any last questions? Okay, well, students, again, the recommendation is that you try to meet together as soon as possible. You each have your teams, names and emails. Please reach out to me if you have any questions or have any trouble connecting with your team. And as Robert said, plan on a preliminary design review for next Friday, the end of next week. And
That's
we'll
internal
also
to your
have-
team. And
Yep.
to your coach should be there. And but you basically have got 2 weeks to do the heart of your design. And then the third week is going to be writing it up. Now you can do design work while you're writing it up. Someone could say, hey, you haven't figured out how much power it's going to take to recycle that much water. And okay, well, we'll work that calculation out as part of that. And then you can have an internal review of the report. Now, I do want to say something to the students here. I don't know, I can't remember whether I mentioned this, but as you can see, this is a very different approach to education than the standard that you've encountered in high school. And I believe it's potentially a very effective form of education. As I say, in all the better engineering schools, this is done. Unfortunately, only to a limited degree, but it is done. And it is a very important part of the curriculum. I think that if we're successful here, if you are successful here, and it's up to you to make this work, you see. You can see that this is only as good as you choose to make it. We will be demonstrating a new model for education that could have much more extensive use and would be of great benefit to students all over the world doing all kinds of things. You've all been in high school and middle school, elementary school, and you've lived through all that. And there's certainly good sides to that, but as you know, there's sides to that are not the greatest. And if we're successful here in this project, we're going to make this known, what happened here, what you did. And it'll be an example that can help reform education in a very positive way, worldwide and for generations to come. So right now, you're part of an experiment that could make history.
Awesome. Okay. Well, unless there's anything, any last questions? We got a heart there from Carl. Thank you, Carl. So your coaches will be in touch with you by midweek next week. And please reach out if you have any questions or need any assistance.
Right. And I suggest you guys get in touch with each other, set up a Zoom call among your group as soon as you can, like today, or if not, then tomorrow. This is the kind of thing, I run an engineering company and I'm doing engineering all the time. I'm doing it at home. I'm doing it in my sleep. I'm doing it, this is not done within set hours, but you got to tear into this. And I should add, by the way, that the winning team will be invited to present at the Mars Society International Conference, which is going to be near Phoenix, Arizona, in October 17th through 20th of this year.
It's actually October 20th to 23rd.
Okay,
Thursday
so
through
it's
Sunday.
been postponed, as you can see. Now, okay, so October 20th through 23rd near Phoenix. Yeah, so tear into it and do a knock-up job and show NASA how it should be thinking about the Mars mission.
Okay. Good luck, everybody. All right. Thank you so much. Again,
Thank you.
feel free to reach out if you have any questions. And good luck. And we'll go ahead and end the call now.
Okay,
Thank you.
thank you. Thanks, everybody.
Have a good afternoon.
James,
too.
do you have a moment for me when everything left?
Yeah. Let me turn off the recording.